Hello guys, welcome to Sri Chaitanya's NEET Sankalp 2.0 program. I am Varaprasad. Today I am going to deal with 3 chapters of modern physics. They are dual nature of radiation and matter, atoms and nuclei. So for discussing these topics, we will select some problems. While discussing the problems, I will discuss the concepts involved in them. First we will go with dual nature of radiation and matter. So here is a problem. The work function of a substance is 4 electron volt. The longest wavelength of the light that can cause photoelectric emission from this substance is approximately. You are all familiar with the fact that when the radiation of frequency more than certain value or wavelength less than certain value is incident on a given metal, then photoelectric emission takes place. That photoelectric emission to take place, the energy of the photon should be greater than work function. That is, hc by lambda should be greater than work function. When you say this lambda is the maximum wavelength, that happens to be the threshold wavelength is equal to, it is hc by work function. But if you are to give, when the work function is given in electron volt, we can go for an approximate relation like 1240 by work function taken in electron volt. We get this in nanometer. So therefore, it is 1240 divided by 4 nanometer, that happen to be equal to 310 nanometer. So this is what is it. So this shortcut relation is useful when you are given the work function or energy of the photon in electron volt. We can go with the wavelength as 1240 by energy of the photon or energy work function in electron volt, so that we will get it in nanometer. If you want to do it in angstroms, it is 12,400 by work function in electron volt or energy of the photon in electron volt, we will get it in angstroms. Let us now see another problem. That is, the surface of a metal is illuminated with a light of wavelength 4000 angstroms. The maximum kinetic energy of the ejected photoelectrons was found to be 1.68 electron volt. What is the work function of the metal? Now we know that the work function of a metal is a constant for a given metal. On any metal, if a radiation of frequency certain value, wavelength or frequency nu greater than threshold frequency is incident, then photoelectrons are emitted. So the photoelectrons emitted happen to have kinetic energies ranging from 0 to Ke max. So according to Einstein's photoelectric relation, maximum kinetic energy of the photoelectron is equal to energy of the photon minus work function. Okay? So here we want to find out the work function of the metal. So work function is energy of the photon. Here we are given the wavelength of the radiation incident is 4000. As I told you earlier, we can go for the shortcut relation and write it as this many electron volt minus the maximum kinetic energy is given in electron volt. So it is 1.68 electron volt. So that we get it to be equal to, it is 3.1 minus 1.68 electron volt. On simplification, we get it, it is 3.1 minus 1.7, if I imagine 1.4, so therefore it is 1.42 electron volt. So this can be the answer, but the options are not given in electron volt, they are given in joule. So we have to convert this into joule, like we know 1 electron volt is equal to 1.6 into 10 power minus 19 joule. That is, the kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt is known as electron volt. Hence, the work function is equal to 1.42 times 1.6 into 10 raised to minus 19 joule. So if you simplify it, is 1.42 times 1.6 is nearly 2.272. We can say it is 2.272 times 10 power minus 19 joule. Actually, having written this, I looked at the options. it is not 1.42 joule, it is not 1.42 into 10 power minus 19 joule. Approximately this is 1.42 times 1.6 is the only value that you can find here is this. Okay. Now let us go for the next problem. The radiation of wavelength lambda is incident on a photometal. Photometal is a surface on which it is photocell. The fastest electron has a speed v and the wavelength changes to 3 lambda by 4. The speed of the fastest emitted electron will be. Already I told you that when on a photometal or a photocell, if radiation is incident, the kinetic energy of the photoelectrons emitted happen to have a range of values. So the kinetic energy ranges from 0 to Ke max. Even the speed also ranges from 0 to V max. So the maximum speed is given this. So from the Einstein's photoelectric equation, Ke maximum is equal to energy of the photon minus work function. This I am writing in my convenient way to solve the question, that is half mv square is equal to, it is hc by lambda minus work function. For a given metal, the work function being same, for the next radiation 3 lambda by 4, first radiation incident is lambda. So next radiation is 3 lambda by 4. The kinetic energy of the fastest electrons changes, let me select it to be V2, is hc by, it is 3 lambda by 4. So 3 lambda by 4 happen to be 4 hc by 3 lambda minus work function. From these two we can arrive at what is required. So if you rewrite this expression, that is half mv2 square is equal to 4 by 3 times hc by lambda. Instead of hc by lambda, I am writing 4 by 3 times. Instead of hc by lambda, I am writing half mv square plus work function. But already in this expression we have minus w. So if you rewrite this expression, it is half mv2 square is 4 by 3 times half mv square plus, it is 4 by 3 w minus w, that is w by 3. So if you compare these two, v2 and v, clearly we can understand that v2 square is greater than 4 by 3 times v square, because we have added something. So to this factor, to 4 by 3 times half mv square, we have added something. Therefore v2 obviously is greater than root over 4 by 3 times root over 4 by 3 times v. So that is among the given options, v2 is greater than 4 by 3 square root of 4 by 3 times v. It should be this answer. Okay. So let us now go for the next problem, that is when the energy of incident radiation is increased by 20%, kinetic energy of the photoelectrons emitted from metal surface increased from 0.5 electron volt to 0.8 electron volt. The work function of the metal is, as I discussed in the previous problem also, when the wavelength is reduced or frequency is increased, the energy of the photons incident will increase and hence the maximum kinetic energy of the photoelectrons will increase, but the work function of the material remains constant, which is a constant of the material, which is a characteristic of the material. So let us now look at this here. Here, when energy of the incident radiation is increased by, so work maximum kinetic energy is equal to energy of the photon minus work function. So in the first case, it is 0.5 electron volt minus is equal to energy of the photon minus work function. Later we increased the energy of the incident photon by 20%. Therefore, in that case the maximum kinetic energy has become 0.8 electron volt as given. That is equal to 1.2 E, I am writing, it is increased by 20%. If it was E earlier, it is 1.2 E minus work function. You are asked to talk about the work function of the material, so we have to eliminate this E. So if you rewrite this expression, it is 0.5 plus W is equal to, it is, we want to write this as 1.2, okay, we can divide or we can, from this we have to arrive at the work function, that is W. So what we can do here is, we better eliminate the energy of the photon. So that means it is W plus 0.5 should be equal to, it is W plus 0.8 divided by 1.2. So on simplification, what we get here is 1.2 W plus it is 0.6 should be equal to 0.8 plus W, that is 0.2 W should be equal to 0.2, all that in electron volt. Therefore, work function of the metal should be 1 electron volt. So here the first option is appropriate. Okay. So in the previous problem and this problem, we use the same concept, that is work function is a characteristic of the metal. If the frequency of the incident radiation is increased, or energy of the photon is increased, or wavelength is reduced, then the maximum kinetic energy varies, it increases. So let us now go for the next one, that is in Lenard's experiment for photoelectric effect, nickel surface is irradiated by ultraviolet light of 200 nanometer. Work function of nickel is 5 electron volt. If the collector is given plus 5 volt with respect to the emitter, then the range of kinetic energy of the photoelectrons on reaching the collector will be. So when this is a photoemitter, Lenard's experiment, if you recall, this is a photoemitter and this is a collector. If this photoemitter is given negative potential or collector is given positive potential, emitter is given negative potential with respect to the collector, or collector is given positive potential with respect to the emitter, then the photoelectrons which are emitted, if there is no potential given to it at all with respect to this is at a zero potential, I mean to say, in such a case what happens is, the range of kinetic energy of the photoelectrons is, as we discussed earlier, that is Ke max is equal to energy of the photon minus work function. But here, because this nickel is given a positive potential plus 5 volt with respect to it, there is an electric field in this direction from collector to emitter. The photoelectrons emitted, they experience force opposite to the direction of the electric field. Therefore, they get accelerated by the electric field. So as they get accelerated by the electric field, there is some additional energy gained by it because of the work done by the electric field. First we will calculate the maximum kinetic energy of the photoelectrons without this applied potential to the collector. That is Ke max, it would have been the Ke max, that is energy of the photon 1240 by 200 minus 5 electron volt. That happened to be, it is 100 times, it is 620, therefore 6.2, that happened to be 1.2 electron volt. So the range of kinetic energies in absence of electric field, would have been 0 to 1.2 electron volt. But this electric field applied, that is giving positive potential to the collector with respect to the emitter, they accelerate all photoelectrons, that is the photoelectrons with 0 kinetic energy and photoelectrons with maximum kinetic energy, everything gets accelerated. Therefore, in presence of this electric field, the range of kinetic energies becomes, that is 5 volt to 6.2 volt, because every electron gets accelerated. as every electron gets accelerated, this electrons with 0 kinetic energy acquire plus 5 volt electron of 5 electron volt, and this becomes 6.2 electron volt. That is 1.2 plus 5 to make you understand, that is 6.2. 5 electron volt to 6.2 electron volt. This would be appropriate answer. Then, if you go to the next one, the figure shows the variation of photoelectric effect with anode potential, a photosensitive surface for 3 different radiations, radiations. Let IA, IB, IC be the intensities, FA, FB and FC be the frequencies for the curves ABC respectively. So, here on a photometal, so anode potential and photocurrent is, that is by varying the anode potential, photocurrent is recorded. You know, when the frequency of the radiation is more than threshold frequency, so if you keep the potential of the collector, which I told you in the previous problem, that is collector or anode, even if it is 0, there is a range of kinetic, the photoelectrons will be emitted with different kinetic energies. So even if you do not apply any potential to the collector, some electrons will reach the collector. So therefore, this photocurrent will have certain value. And if you go on increasing the applied potential, they get accelerated, so more and more photoelectrons will reach the collector, and photocurrent goes on increasing and reaches a constant value. This is called saturation photocurrent. Okay. And if you reduce the potential, apply the negative potential to the collector or positive potential to the emitter, then photocurrent goes on decreasing and becomes 0. This potential at which the photocurrent becomes 0 is called as the cutoff voltage, stopping voltage, we can say even stopping voltage. So this saturated current depends upon intensity of the radiation. The saturation current, if you have a radiation of same frequency but of higher intensity, what we are making it do is more number of photons are made to incident per unit area per unit time. Therefore, even with 0 potential applied, the number of photoelectrons with maximum kinetic energy would increase, therefore photocurrent would increase. Again, with increase in applied potential to the collector, the photocurrent goes on increasing, saturation current will be higher than the previous value. But if you are talking about the radiation of same frequency, we did not change the frequency of the radiation. Okay, we did not change the metal. These two are kept fixed. As metal is kept fixed, the stopping potential remains constant. As frequency of the radiation is kept fixed, the energy of the photons is kept constant. Only what changes is the number of photoelectrons emitted changes as the number of the photons made to incident happen to be changed. So with higher intensity of radiation, more number of photons are made to incident and hence more photocurrent is possible. But this stopping potential remains same. Why? Because according to Einstein's photoelectric relation, Ke maximum is equal to, it is energy of the photon minus work function. So if you write this as EV0, so that is kinetic energy, maximum kinetic energy, if you write it as EV0 is equal to, it is energy of the photon minus work function. So here, as we did not change the energy of the photon, as we did not change the metal, that is work function, the stopping potential remains constant. So anyways, with this concept we will be able to answer this. Here for the radiation B and A, the saturation current is found to be same in both cases. From this we can clearly understand that saturation current is incident on the intensity of the radiation but not on the frequency of the radiation. Therefore we can say the IB and IA, that is intensity of the radiation B and A, are equal. IB is equal to IA. And here the saturation current in case of the radiation C is greater than these two cases. Therefore IC is, intensity of the radiation C is greater than these two. So IC is greater than IB is equal to IA. And if you see, this is stopping potential. So stopping potential is given to be same in case of B and C, which is greater than the stopping potential of A. So in the figure, I want to make it clear that the stopping potential of B and C are greater, more negative value, I mean to say. Okay. So therefore, and B and C is more negative than A, but for B and C it is same. Stopping potential is same in the sense, so we can say the frequency for a given metal phi is constant, but we must have increased the frequency of the incident radiation compared to A. So frequency of C is equal to frequency of B, but that is greater than frequency of A. Why? Because the maximum kinetic energy of the photoelectrons emitted in case of the radiation A is less, stopping potential is less. So this relation we have to look at. So Fc is equal to Fb is greater than Fa, Fc is equal to Fb, one relation we got it, okay. So therefore this is then, and also Ib is equal to Ia, so only relation is this. But actually if you are compared to with other also, we can arrive at this relation, Ic is greater than Ib, and also we can say Fc is equal to Fb, which is greater than Fa, okay. Then let us go for the next problem. In an experiment of photoelectric effect, the slope of cutoff voltage versus frequency of incident radiation is found to be 4.15 times 10 power minus 15 volt second. Value of Planck's constant is, when you are asked to talk about Planck's constant, don't jump to a conclusion that it should be given with what you have learned as a fact, that is 6.625 into 10 power minus 34 joule seconds, because some data is given and from that data you have to answer that. So we know that cutoff voltage or stopping cutoff voltage and the frequency of the radiation, that is again maximum kinetic energy of the photoelectron according to Einstein's photoelectric equation. So maximum kinetic energy of the photoelectrons is equal to h nu minus work function, okay. So this maximum kinetic energy, I already told you that it can be given by EV naught, can be written as h nu minus work function. Therefore stopping potential V naught is nothing but h by E times frequency of the radiation minus work function by E. Work function I write either by phi or W, it makes no difference, it is a constant for a given metal. So if you look at this equation, it is in the form of y is equal to mx minus c. So if you plot a graph of frequency, that stopping potential versus frequency, it will be a graph like this. So taking frequency on x-axis and stopping potential on y-axis, the graph is like this. So this intercept on frequency axis indicates the stopping potential, threshold frequency, and it has a negative intercept. If you extend it, it is a negative intercept on stopping on potential axis. But here from this equation we can clearly understand this is the slope. So we have to make use of it to get the required answer. That is, slope is given to be slope we got it to be h by E from this. The slope value of the slope is given to be 4.15 times 10 power minus 15. It is 4.15 times 10 raised to minus 15 is equal to, it is h, and we want to find out the Planck's constant itself. The value of the charge of the electron is known to all of you, so that is 1.6 times 1, okay, it is 1.6 times 10 power minus 19. So this many, this is h. So if you simplify it, we will get this approximately equal to, it is 4.15 times 1.6 is nearly 6.62 or 6. Okay, so it is, yeah. So it is 10 power minus 34 that is 10 power minus 34, 4.15 into 10 power minus 34 joule seconds is not correct answer. And it is 6.625 into 10 power minus 33 joule seconds is not correct. So therefore, the only possibility is 6.64 into 10 power minus 34 joule seconds, because we get it to be order of 10 power minus 34, 10 power minus 34, there are only two answers here. One is 4.15 into 10 power minus 34, the other is 6.64 into 10 power minus 34. If at all they are given to be very close values, you have to simplify that multiplication properly and then arrive at the answer. Let us now go to the next one. The energy flux of sunlight reaching the surface of the earth is 10 power 4 watt per meter square. So the average wavelength emitted by sun is 550 nanometer. How many photons are incident per second per square meter of the earth's surface? Probably you must have heard of it. This is as a solar constant, but anyways, we don't need to worry about that. So here it is given to be how much this energy, this is in watt per meter square, is nothing but intensity. So intensity in case of this is given by number of photons incident into energy of each photon divided by the area on which they are incident times the time. That is, if n photons each of energy EPH are incident in a time t on an area A, then the intensity is given to be I. So that is what we have to find out. So here number of photons incident per square meter on the earth. Okay. So the average wavelength per square meter of the earth. So here we can look at this energy of the photon also we can write it as n into, it is a hc by lambda into at, we can write it. So if you try to simplify using this data, probably will take lot of time. So therefore again we can go for an approximate shortcut relation, that is hc by lambda we can take from that 1240 by 550, so that we will get it in electron volt. Okay. So therefore it is given to be it is given to be 10 power 4 watt per meter square in SI it is given. So therefore it is n by t is required, n by TAT is required, because number of photons incident per second per square meter. So n by AT is required. So this we can write it as, it is 1240 by 500, but we get it in electron volt. So that electron volt is to be converted into the joule. It is 1.6 times 10 power minus 19. Then we will be able to get it, that is, so we can say it is approximation. Let us go for approximations. That is 5 by 124 times 16, or we can write this way. We can make use of another shortcut relation. So let us look at this. Here the energy of the photon is equal to let me as I told you, intensity is number of photons into energy of photon by area into time taken. So what we require is this number of photons incident per unit area per unit time. So therefore it happens to be 10 power 4 is equal to n by AT into energy of the photon. We can write it as hc by lambda, or we can write it as 1240 by, it is 550, it is this many electron volt, but this is given in SI, so we have to go for this into this multiplied by 1.6 times 10 power minus 19. So if you simplify it, what we get here is n by AT should be equal to, it is 10 power 4, it is times 55 by 124 into 1.6. So here we can make use of this 1 by 1.6 into 10 power minus 19. You are familiar with this fact that this 1 by 1.6 times 10 power minus 19 is 6.25 into 10 power 18. So therefore it is 10 power 4 times 55 by 124 into, it is 6.25 into 10 power 18. If you write that way, the simplification becomes easy, because we learned it in the electrostatics. The number of electrons present in 1 coulomb of charge, if you have to calculate it, is 1 by 1.6 into 10 power minus 19. We learned it as a fact like 6.25 into 10 power 18. We can make use of that and simplify it quickly. So here we can go with an approximate answer, that is, it is 25 5s are 25 25s are 0.25, we can write it. So it is 5 11 times. So 11 times 0.25 is 55, 11 times 2, 6, it is approximately, we get it to be 2.5 something, that is very close to that 2.78 only. So 2.78 times, it is 10 power 14 and 10 power 4 and 10 power 18, that is 10 power 22. We can arrive at the answer like that. So then if you talk about an electron is accelerated through a potential difference of V volt, if the de Broglie wavelength of the electron is 1.227 in 10 power minus 2 nanometer, the potential difference is. So we know that according to de Broglie's hypothesis, every particle having momentum behaves like a wave of wavelength lambda, given by lambda is equal to h by mv. Okay, lambda is equal to h by momentum or h by mv, that is equal to h by root 2 km, where k is the kinetic energy of it. Also we arrive at a relation, very shortcut relation. If an electron is accelerated through a potential difference of V volts, we can make use of this relation, no doubt, but it becomes lengthy. But we learn a shortcut relation, 12.27 by root V angstroms, we get it. Okay, so we can make use of this relation to arrive at the answer, like you are given that root V is equal to, it is 1.227, because I have written here in angstroms, but it is given to be in nanometer. So 1.227 by, it is, the wavelength is given to be 1.227 times 10 power minus 2 okay, nanometer. This is, so we get it in volt. So here it is, it is square root of volt, I mean to say, because I have already written. So it is, you get it to be 10 power 2, but we want potential difference that happen to be 10 power 4 volt. So we can make use of this shortcut relation which we have learned, like lambda, when an electron is accelerated through a potential difference V volt, the de Broglie wavelength of it is given by 12.27 by root V angstroms, or 1.227 by root V in nanometer. Then, so the light of whose photons have energy 3.8 electron volt illuminate two different metallic surfaces whose work functions are 0.6 electron volt and 1.4 electron volt respectively. The ratio of de Broglie wavelength of electrons emitted with maximum kinetic energy from the two metals. Here the question is a combination of the photoelectric emission and the de Broglie wavelength. So again, so maximum kinetic energy of the photoelectrons happen to be equal to energy of the photon minus work function. So work function of the metal is given to be, there are two different metals, the light of photons, same radiation is made to incident on two different metals. So therefore maximum kinetic energy changes though the photons of same energy, because work functions are different. So maximum kinetic energy in the first case divided by maximum kinetic energy in the second case are, it is 3.8 times work function of the first metal 0.6, and it is 3.8 minus, it is 1.4. So it happens to be it is 3.2 divided by, it is 2.4. That happened to be 12 twos are 12, no, not 12. So here, yeah. So what is that we get here is, it is 32 by 7, 4 8s are 4 6s are 8, 4 6s are. That happened to be 4 by 3 rather. So this is the ratio of maximum kinetic energies. But already I told you that the de Broglie wavelength is given by lambda is equal to h by mv or root 2 km. We are talking about the electrons only in both cases. Therefore, mass of the electron particle is same in both cases. Therefore, lambda 1 by lambda 2, that is maximum, that is de Broglie wavelengths. De Broglie wavelengths are in the inverse proportions of the square root of the maximum kinetic energies k2 by k1, that happen to be 3 by 4. That is, it is 3 is to root 3 is to 2. This is third option is possible. Then, if you go to the next one, an electron of mass m moving with initial velocity v bar is equal to v naught I cap plus v naught j cap is in an electric field. E bar is equal to E naught k cap. If lambda naught is the initial wavelength of the electrons, its de Broglie wavelength at a time t is given by. Initially with this speed, with this velocity v bar is equal to v naught I cap plus v naught j cap, it has a wavelength given by, de Broglie wavelength given by lambda naught is equal to h by m into root 2 v naught. When we are writing this momentum, magnitude of momentum only we have to write it. So I say it should be root 2 v naught. Now, because of the electric field, the velocity of the electron changes with time. So velocity v2 bar, if you write it as, the initial velocity factor, initial velocity is not affected because the electric field happened to be acting only along k cap, along z axis. So here initial velocity is along x axis, it has components along x axis as well as y axis. Therefore, that remains as it is, v naught I cap plus v naught j cap plus, okay, it is an electron, so therefore it gets accelerated opposite to the direction of the electric field. So therefore, it is minus, okay, so minus, it is v is equal to at, that is, it is E by m minus E naught E by m t k cap. I repeat, because of the electric field, it gets accelerated opposite to the direction of the electric field. So as the electric field is given to be along minus k cap, it should be plus. Okay, so it is V is at, A is nothing but force by mass, force by the electric field is E naught E by m, E naught E, then there is E naught E by m. So therefore speed becomes, it is a root over, it is V naught square plus V naught square plus this, that is 2 V naught square plus, it is E by m into t whole square. This is the new speed. Therefore, the new wavelength happened to be h by m times root over 2 V naught square plus E t by t by m whole square. So therefore, we can rewrite this expression in the term required, in the way required. We can bring out this 2 V naught square outside, okay, root 2 V naught can be brought out. So therefore, what happens is here, this is h by m into root 2 V naught, so that we can get it as 1 plus, it is E square, capital E square, t square by 2m square v naught square. So, whole power half or square root of it. So, among the given, this will be proper answer. Why? Because all this can be written as, so all this can be taken as lambda naught. So, therefore, lambda naught by root over 1 plus e small e square capital E square t square by 2m square v square will be the appropriate answer. Now, let us see the next problem, that is, earlier we have seen that electron got accelerated in the electric field, but now charged particles accelerated in magnetic field is given the situation. If an alpha particle, a proton and an electron are moving with same radius in a uniform transverse magnetic field, with the same radius in a uniform transverse magnetic field, then their respective de Broglie wavelengths are. We will be able to recall the revolution of a charged particle in a magnetic field. If a charged particle is projected in a transverse magnetic field, is moving in a magnetic field, it moves in a circular path of radius r, given by r is equal to mv by qb, that is root 2 km by qb, etc. we can write it. But here that is nothing but momentum by qb. Because we are now talking about the de Broglie wavelength, we are to look at the momentum. De Broglie wavelength is given by lambda is equal to h by p. So, instead of this p, we can write h by lambda. Therefore, we can write p is equal to qbr, also p is equal to h by lambda. qbr h by lambda. So, our task is to compare the wavelengths and the, I write again. So, from this p momentum of the charged particle is qbr, and from this we can write momentum to be equal to h by lambda. Our task is to compare the wavelength with charge, because they are moving in the same transverse magnetic field with same radius. So, these two are same, and this is anyway constant. Therefore, lambda is inversely proportional to q. Here alpha particle, proton and electron are given. Proton and electron, they have same charge. We don't need to worry about the mass of it. Here it is just inversely proportional to charge. So, therefore, the sense of revolutions might be different, but the wavelengths will be same. So, lambda for proton and lambda for electron will be same, okay? But here charge of the alpha particle is twice that of the proton. Therefore, we can say, therefore, lambda proton is lambda electron, and this is being charge greater for alpha particle, which is twice that of the proton. We can say that wavelength is smaller. So, these two have a greater wavelength than alpha particle. So, alpha proton is equal to alpha electron, but that is lambda proton is equal to lambda electron, but lambda of the alpha particle is smaller. The only possibility is here. Then, if you go to the next problem, a particle of mass m, which is particle A of mass m, so now let us see the second chapter, that is atoms. While discussing the problems, let us recall the concepts related to them. Here the first problem says, if Vn and Rn denote the velocity of electron and radius of nth orbit of hydrogen atom respectively, then the ratio of Rn to Vn is in successive orbits is. You are all familiar with the fact that the radius of the electron in the nth orbit of hydrogen atom is given by, it is 0.529 n square by z, where n is the principal quantum number or number of the orbit and z is the atomic number. If it is valid for, because Bohr's model is valid for not just hydrogen atom, hydrogen like species it is valid, that is He plus ion, Li plus 2 ion, etc. Okay? So this is a general expression. And also velocity of the electron in the nth orbit is 2.18 into 10 raised to 6 into z by n, it is meter per second. So our task is to talk about Rn to Vn, the ratio of Rn to Vn. So Rn to Vn in the same atom, so therefore Z remains constant, and all this is, anyway we are talking about the proportions, it is n square by z times it is n by z, because Rn by Vn we have to write. So n cube in the sense it is 1:2, in the successive orbits it is 1:2, 2 cube is 2, 3 cube is 2, so on. This is the answer. Then if you talk about the next one, that is angular momentum is L1 of an electron in the ground state of hydrogen. What will be the angular momentum of the electron in the second orbit of helium? From angular momentum quantization condition, the angular momentum of the electron in the nth orbit of hydrogen atom or hydrogen like species is given by L is equal to, it is mvr by expression, it is nothing but nh by 2 pi. So it is not dependent on whether it is hydrogen atom or helium like ion, it is just dependent on the principal quantum number itself. Therefore L1 by L2, L1 is given to be L1 itself, it is in hydrogen atom in the ground state, so principal quantum number is 1. In the second angular momentum of the electron in the second orbit of hydrogen atom, it is given to be 2. So therefore L2 should be equal to 2L1. So this is appropriate answer. Then if I talk about the next problem, an electron revolves around the nucleus in first orbit of hydrogen atom. The magnitude of its linear momentum in this motion is, you are now asked about linear momentum, not the angular momentum. Okay? So it is revolving in the first orbit of hydrogen atom. So we want to find out the linear momentum. We can do it in this way, angular momentum quantization condition, L is equal to mvr is equal to nh by 2 pi, we can make use of this. We want to find out the angular linear momentum mv. So therefore linear momentum mv is equal to nh by 2 pi r, we can write it and simplify this. So here momentum in the first orbit, it is asked, so it is principal quantum number is 1 and it is 6.625 into 10 power minus 34, because the answers are given in SI, times by 2 pi into, it is a radius of the electron in the nth orbit of hydrogen atom is 0.529 angstroms. So it is this many kg meter per second we get it. So we can arrive at an approximate answer. So this is 3.14 times 2 is 6.28. So it is slightly more than 1, we get it. 1 divided by 0.529 is approximately, if you take it, it is 2, very closely 2, not exactly. So it is very closely 2 times, it is 10 power minus 34 divided by 10 power minus 10 is 10 power minus 24 kg meter per second. So among the given options, this is possible answer. If the answers are given very close to each other, then we have to obviously go for, because it is 2 into 10 power minus 24, 4 into 10 power minus 24. So approximately we get it to be 2, not 2 point something. If there is some other answer, then we would have actually carefully looked at the simplification. So the time period of revolution of electron in its ground state orbit in hydrogen atom is 1.6 times 10 power minus 16 seconds. The frequency of revolution of the electron in the first excited state is, so here time period of revolution, whenever a particle is revolving around another particle under the influence of centripetal force which is varying inversely as a square of the distance, then that is if the centripetal force obeys the inverse square law, then as in gravitation we can write T square is directly proportional to R cube, where T is the time period of revolution and R is the radius of the orbit in which it is revolving. It is valid for satellites revolving around the earth, it is valid for electron revolving around the nucleus. In hydrogen atom we can, as we are discussing. So, but we know radius of the electron is directly proportional to, it is 0.529 n square. So, therefore, it is directly proportional to this. From these two we can write T is directly proportional to R to the power of 3 by 2. So, therefore, T is directly proportional to n cube, we can write it. Time period of revolution of electron in the nth orbit of hydrogen atom can be written this way. So, therefore, it is time period in the first orbit divided by time period in the second orbit, because it is given to be first excited state. So, can be taken as 1 by 2 cube. But we want a reciprocal of this T2 because we want frequency, not time period. So, 1 by T2. 1 by T2 should be equal to, it is 1 by T2, if I retain like this, it is 1 by 8 times that T1. T1 is given to be 1.6 times 10 power minus 16. So, if you simplify this, you get it to be in hertz or per second, whatever it is. So, it is 10 power 15, first of all 10 power 10 times 10 power 10 times 10 times 10 power 14, the way you can simplify this way, 8 into 1.6. It is 1.25 times. So, if it is 1.25 times, approximately this is, you get it to be equal to, this is 3 times, 4 times, very close values I am talking about. This is 2.5. So, it is 7.5 times 10 power 14, that is the closest answer is 7.8 into 10 power 14. Okay? You can approximate answers can also be found, and we can write this many hertz or this many per second. Okay? Then let us look at another problem. The relation between magnetic moment mu of a revolving electron around the nucleus with principal quantum number n is the relation between the magnetic moment and the principal quantum number is asked. We know that magnetic moment mu is nothing but, it is okay, we can make use of the gyromagnetic ratio. What is gyromagnetic ratio? The ratio of magnetic moment to angular momentum is given by, it is q by 2m. Okay? So, we can make use of this relation to arrive at the answer quickly. So, mu is equal to E by 2m, because we are talking about electron in the hydrogen atom. It is L is equal to, it is NH by 2 pi. So, therefore, magnetic moment is directly proportional to principal quantum number, we can write it. Rather, we can familiarly write this E by 4 pi m, okay, EH by 4 pi m times n. So, this is what is Bohr magneton, you are all familiar with that. So, therefore, magnetic moment is directly proportional to the principal quantum number. Then, if you go to the next one, when a hydrogen atom is raised from the ground state to an excited state, what happens to its potential energy, kinetic energy, total energy, etc., is a very, very familiar fact. Let us recall the energy level diagram. That is, if this is the these are the energy levels. So, this is principal quantum number 1, this is 2, this is 3, 4, 5, you can go on writing it. So, the energy of the electron in the first orbit or ground state is minus 13.6 electron volt, and it is minus 3.4 electron volt, and it is minus 1.51 electron volt. It is minus 0.85 electron volt. You can go on writing it. It is a total energy. Also we know for a particle, the centripetal force, if it varies inversely as a square of the distance, is okay. So that is centripetal force is provided by some source which varies as inversely as a square of the distance. In such a case, the potential energy is to total energy is to kinetic energy ratio is -2 is to -1 is to 1. This is valid for electrons revolving around the nucleus and satellites revolving around the earth. So therefore, as we go from the lower orbit to higher orbits, the negative value of the energy is decreasing. Even potential energy, if you write it, what is the potential energy here? Let us say the potential energy here is 2 times this, that is minus 27.2 electron volt, minus 6.8 electron volt, minus 3.02 electron volt, etc. As we go to the higher orbits, it is going on decreasing. Potential energy decreases, total energy decreases. In the infinite energy level, both potential energy and kinetic energy are zero each. Potential energy and total energy are 0. Kinetic energy anyway will be 0. So as you go to higher orbits, here kinetic energy, if you write here, I am writing kinetic energy here with this, okay. So kinetic energy is equal in magnitude to the total energy. So therefore, it is plus 13.6, it is plus 3.4 kinetic energy. This column is indicating plus 13.6 electron volt. This is plus 3.4 electron volt, this is plus 1.51 electron volt, etc. That is where the total energy, the summation of this potential kinetic energy and potential energy happen to be 13.6. So as you go to higher energy levels, what is happening is kinetic energy decreases, potential energy increases and total energy also increases. So potential energy increases, kinetic energy decreases is correct. Both kinetic energy and potential energy increases false. So this is correct answer. Potential energy increases, kinetic energy decreases. Okay. Then let us go to the next problem, that is the transition from n is equal to 3 to n is equal to 1 in a hydrogen atom like results in ultraviolet radiation. Infrared radiation will be obtained in the transition from, some options are given. Let us check. We know that the electrons, when they get de-excited from higher energy level to lower energy level, a photon whose energy is equal to energy difference between the energy levels is given. So in the hydrogen atom, we get Lyman, Balmer, Paschen, bracket, Fund series. So if the electrons, if they get excited from higher energy level to first energy level, then we get Lyman series, that is principal quantum numbers 1, 2, 1, 2, 3, 4, 5. So if the electron gets de-excited from higher energy level to first, we get Lyman series. This Lyman series is possible in ultraviolet region, and we know that if they get excited from higher energy level to second energy level, we get Balmer series. They are possible in the visible region. If they get de-excited from the higher energy level to third energy level, Paschen series, this is possible in infrared region, and bracket and Fund are possible in far infrared region. So we want to talk about infrared region possibility. That means electrons have to get de-excited from higher energy level to third energy level. So here the transition from n is equal to 3 to 1, obviously that is in ultraviolet region, because it is a Lyman series in ultraviolet region, as I told you. Okay. Now this is in visible region, this should be in ultraviolet region. Let us check that. So here ultraviolet radiation, we want to get ultraviolet radiation. So when is possible? When it is getting de-excited from 4 to 3 or 5 to 3, etc. There is no answer possible among the given. Had it been given as 4 to 3, then this is possible answer. Even if you use the energy values that I have told you, 4 to 2 is not possible. Okay. So as I told you, it is minus 13.6 minus, it is 3.4, it is minus 1.51 minus 0.85. So if you say from this orbit to this orbit, it is approximately 2.6 electron volt, and the wavelength corresponding to the 2.6 electron volt is 12,400 by 2.6. If you write it approximately, that you get it to be equal to it is 2.5, so it is 26. If I put this way, it is approximately 5,000. 25 5s are 125. I am going a very closer value. It is not exactly 5,000, but it is a little less than 5,000 angstroms, which does not belong to ultraviolet region. So therefore, there is no correct answer. Had it been 423, then it would have been correct. Then let me go for the next one. The energy levels for an electron in certain atom are shown in the diagram. Which of the following transition gives emission of a photon with most energy? So here there is no emission of photon when you talk about 1, 2, 3, because it is getting excited. When it is getting excited, there is an absorption of energy. There is no emission of energy. And here in this case, de-excitation from 4 to 3, 4 to 2 and 2 to 1 are possible, they are. But in this case, as we learned, if it is a hydrogen atom, it is minus 13.6 minus 3.4 electron volt minus 1.51 electron volt minus 0.85 electron volt. If you see the difference between these two, it is actually, they are somewhat closely spaced compared to this. This is 10.2 electron volt. The difference is 10.2 electron volt. So therefore, photon corresponding to that will have greater energy compared to these two. It is from this to this, it is approximately 2.6 electron volt. So this is 10.2 electron volt. Energy difference will obviously give here between these two, as I told you, it is delta E is nearly 2.6 electron volt. That is a smaller value compared to this. Obviously, this will give a photon with a higher energy. Then let us look at this. The recoil speed of hydrogen atom after it emits a photon in going from n is equal to 5 to n is equal to 1 state. So the electron in the hydrogen atom got de-excited from some higher energy level to lower energy level. In this process, obviously, it gives out a photon. Okay? So we can apply the law of conservation of linear momentum to this. So initially the atom is at rest. So if the atom is at rest, from law of conservation of linear momentum, we can say initial momentum of the system 0 is momentum of the photon plus momentum of the residual hydrogen atom. Okay? So momentum of the photon P is equal to E by C, that is mass of the hydrogen atom into velocity of hydrogen atom is equal to minus by, because vectorially if you talk about scalar relation, then we don't need to write this. So here it is mv is equal to photon, momentum of the photon is energy of the photon by C, because energy of the photon EPH is equal to PC. We have to make use of this relation. Okay? So here velocity of the recoil velocity of the hydrogen atom is energy of the photon emitted. What is energy of the photon emitted? It got de-excited from 5th orbit to 1st orbit. We can calculate that using this relation 13.6 into 1 minus 1 by n square, that happened to be 5 square. This many electron volt, but answers are given in meter per second SI. So therefore, you can write it as 1.6 into 10 power minus 19 whole divided by this C stands for velocity of light, which is 3 times 10 raised to 8. This many meter per second we get it. So this is, it is 13.6 times 24 by 25 times 1.6 divided by 3 here into, it is 10 power minus 19 by 10 power 8, that happen to be okay. Yeah. Oh, here we have mass of hydrogen atom also we have to consider, that happen to be 1.6 into 1.672 into 10 power minus 27. So it is 1.672 also I am writing, and 10 power minus 19 by 10 power minus 19, that is 1. So if you simplify it, what we get here is this one approximation. We can go for a very close approximation. This get cancelled. This is also approximately 1. So it is something like 3 4s are 12, 4, 4.4. Very close answers if you observe. Oh, there are 4.34 and 4.17. So we have to be a little careful. So let us recheck that. Okay, so here let us now go for the simplification again. So here it is 13.6 times 24 by 25. It is 1.6 by 1.672. It is 3 and it is 1, okay, 10 power minus 27, 10 power minus 27. So it happens to be slightly less than 1. It is 4.4. So it is slightly more in the denominator than 4.4. Therefore, it should be less than that, but not a very great value. Therefore, we can say it is to be equal to 4.17 meter per second. Close approximations. Okay. So with this, I can say I have completed the basic problems that we come across in atoms. Guys, let us see the third chapter as we discussed earlier, that is nuclei. So let us discuss the numericals along with the concepts related to them. So the first numerical is, if the radii of nuclei aluminum 1327 and zinc 3064 are R1 and R2 respectively, then R1 by R2 is. The radius of the nucleus is directly proportional to cube root of the mass number, and it is given by R is equal to R naught into a to the power of 1 by 3, where R naught is a constant which is nearly 1.2 Fermi, that is 1.2 into 10 power minus 15 meter. So our task is to compare the radii of the two nuclei with the mass numbers 27 and 64. So R1 by R2 is, it is cube root of, it is 27 by 64, that happen to be 3 by 4. So the second option is correct. Let us now look at the second numerical, that is a nucleus at rest explodes into two nuclei. If they fly off with speeds in the ratio 8:125, the ratio of their nuclear radii is. So if a nucleus at rest explodes into two fragments, it is because of internal forces. Therefore, law of conservation of linear momentum is varied. Therefore, this fragment, if it flies off with a velocity p1 bar, this fragment will fly off with a velocity, with a momentum p2 bar like this. So from law of conservation of linear momentum, the initial momentum of the nucleus is 0 is equal to p1 bar plus p2 bar. So that is, by scalar relation we can write m1 v1 is equal to m2 v2. So therefore, the ratio of the masses of the fragments m1 by m2 is in the inverse proportions of the speeds v2 by v1. And mass of the fragment is directly proportional to mass number. Therefore, we can write this first, it is a1 by a2 happen to be in the inverse proportions of 128 and 125, that is 125 by 8. So, but already we learned that the radius of the nucleus is given by R naught into a to the power of 1 by 3. So from this we will be able to get the R1 by R2 ratio is cube root of, it is 125 by 8, that is 5:2. So third option is correct. Let us now look at the third numerical. The value of binding energy of the value of binding energy per nucleon of calcium 2040 nucleus is. In the formation of calcium 2040 nucleus, the mass of the calcium 2040 nucleus will be less than the constituent nucleons of it. So that mass defected will convert it to energy according to Einstein's mass energy relation, and that energy is called binding energy. Binding energy per each nucleon is the binding energy per average binding energy. That is, binding energy per nucleon is nothing but the mass defect times c square divided by mass number. What is mass defect? Expected mass, that is, there are Z protons, Z into mH, mass of each proton, plus A minus Z times mass of neutron, that is all expected mass of the nucleus, minus mass of the real mass of the nucleus, this divided by, this is all mass defect, this divided by A is mass defect per nucleon, this is to be multiplied with c square. So here first we shall calculate the mass defect. Here calcium 2040, that is the number of neutrons and the number of protons, each is 20. Therefore, we can say 20 times mass of proton, which is given to be 1.007825, and mass of neutron is 1.008665 AMUs. Okay, all this divided by mass number is 40 times minus, okay, minus the real mass of the nucleus is given to be, it is 39.96, 962,589. Okay. So all this you get it in AMU, but that is to be multiplied with 931.5, 931.5. That is to be multiplied with 931.5 million electron volt. Okay. So this is to be multiplied with 931.5 million electron volt. So that you will get the value in, you will get the value in million electron volt. So this is a tedious calculation. Okay. So if you calculate it, you will get the answer, but we don't need to go for simplification. Looking at the options, we get it as 18.32 million electron volt, 8.55 million electron volt, 9.94 million electron volt, 14.72 million electron volt. We know in the average binding energy versus mass number curve, that is binding energy per nucleon versus mass number curve. So the curve is like this. So it is fairly large for the nuclei with mass numbers 30 to 170, and it is very small, it is small for nuclei with mass numbers less than 30, and it decreases, and it is less for the nuclei with mass numbers beyond 170. That is why here the average binding energy of the nuclei with 30 to 170 is fairly large. It is nearly 8.5 million electron volt, and in case of the nucleus ferrous 56, it is highest average binding energy 8.75 million electron volt. Knowing these facts, we will be able to arrive at the answer quickly. That is, no binding energy per nucleon like 18.32 or 14.72 or 9.94 million electron volt are possible. The only possibility is 8.8855 million electron volt. Actually the mass number is 40, so it lies in the range of 30 to 170. If there is only value like 8.5, closer to 8.5, we can select it without actually solving the question. But if the answers happen to be given like 8.5, 8.55 and 7.98 etc., they are given, obviously we will have to simplify this. The whole of the simplification will only give you it, which is a tedious calculation. Okay, then let me talk about the next one. Here lithium 7 fuses with a proton according to the nuclear reaction given by proton plus lithium 7. Let us now discuss the next problem, that is lithium 37 fuses with a proton according to the nuclear reaction given by proton plus lithium 37 is equal to 2He4. So in this kind of questions, if you want to find the Q value, we have to look at the total mass of the reactants and total mass of the products. Total mass of the reactants is sum of the mass of this particle and mass of this particle, that happen to be 1.007825 AMU plus it is 7.016004 AMU. So summing them up, we get 9, it is 2, 8, 13, 2, so 8.02329 AMU. And total mass of the products is 2 alpha particles or 2 He nuclei, so that is 2 times it is 4.002603 AMU, which you get it to be 2 3s are 6, 0, 12, 2 2s are 4, 1, 5, okay, 0, 0, 0, 8 point. So from this we will understand that the total mass of the products is less than the total mass of the reactants. That means some mass must have been defected, and according to Einstein's mass energy relation, that gets converted into energy. So therefore mass defected, if you calculate it, that is 8.023. I am going for the second decimal, third decimal, so I write it as approximation. So 8.234, instead of 238 I am writing 8.024, and here it is 8.005. So approximately this mass defect is equal to 0.19. So as it is 0.19 AMUs. For each AMU we get 931.5 million electron volt. Therefore the Q value, which is released energy, is given by 0.019 times 931.5 million electron volt. So if you take it as approximately 0.2, it is, we get it to be slightly 18 point, I mean if you simplify this, it is very slightly 17.35 million electron volt we get it. Okay. Then because it is 18.06 is obviously greater than this. So therefore slightly less than that we get to be 17.35 million electron volt. Now let us see the next problem. Here assume that the nuclear binding energy per nucleon versus mass number is as shown. It is an assumption. So here the binding energy per nucleon for mass numbers 0 to 100 is 2 million electron volt, from 100 to 200 is approximately 8 million electron volt, and from 200 and beyond it is something like 4 million electron volt. Okay. So as we discussed already, the average binding energy per nucleon, that is binding energy per nucleon versus mass number curve, it happened to be like this. It is for nuclei below 30, okay, it is mass number 30, that is small, and from 30 to 170 it is fairly large, it is nearly 8.5 million electron volt. Beyond 170 it is again decreases. So the nuclei with smaller mass numbers, that is mass numbers less than 30, they try to fuse and they try to get the average binding energy to be greater, so that they bring their binding energy per nucleon into this region. For example, if a nucleus with mass number 20 and nucleus with mass number 25, they fuse, we get a nuclei with mass number 45, which happen to be lying in this region. So the average binding energy increase, so stability increases. And similarly, the nuclei with mass numbers greater than 170, they undergo fission. For example, uranium-92-235, it splits to give barium and krypton, whose mass numbers lie between 30 to 170, hence average binding energy increased and stability increased. So fusion of the nuclei with less than mass number 30 and the fission of the nuclei with mass number greater than 170 is again to see that their average binding energy of the products is greater than the reactants, hence to get the stability. So based on this concept, one assumption is given here. So from this, what is possibility, we have to look at fusion of two nuclei with mass numbers lying in the range 1 less than A less than 50 will release energy. For example, 1 less than A less than 50, that is 1 to 50. Let us say one mass number is some 10 and one mass number is some 40. Okay, let us say 50, it's less than 50, so 49. What is the total mass number? It is 59. 59 happen to be less than 100, therefore there is no increment or decrement in the average binding energy, therefore no release of energy. Will release of energy is not correct. Okay. Now let us look at the next one, next option. We have to go with options. Here fusion of two nuclei with mass numbers lying in the range 51 to 100 will consume energy. See, let us check with some mass numbers, let us say 60 and let us say some 80. If they fuse, they fuse to give out one particular nuclei. So then 140. 140 happen to be obviously lying in the range from 100 to 200, binding energy increase, therefore there is a release of energy. So therefore this is also false. Let us now look at the next one, that is fission of nuclei lying in the mass range 100 to 200. Here 100 to 200 will release energy when broken into two equal fragments. Check with some nuclei 150. Between 100 to 200 we are talking about, 150. If it splits to give two nuclei, two particles with 75, mass number 75 will get it. So here the binding energy of the nuclei with mass number 100 to 200 is fairly large, 8 million electron volt, and if it is below 100 it is less, 2 million electron volt. Obviously there is a release of energy here, so therefore it is correct. Okay. Now let us talk about the fourth option also. Fission of a nuclei lying in the mass range 200 to 260. 200 to 260, this is okay, that is splitting to give two nuclei. You check, okay, some equal fragments, again it is given to be equal fragments. Let us check some 240. 240 if it splits to give two nuclei with mass numbers 120. So here average binding energy is 4 million electron volt and that is giving out two nuclei with average binding energy, so lying as 8 million electron volt. Therefore there is no see here release of energy when broken into two equal fragments, though therefore what we can say here is also there is an energy. Okay. Then let us now look at the next question. Two lighter nuclei combine to form comparatively heavier nucleus by relation given by X12 plus X12 gives rise to Y24. The binding energy per nucleon of X12, Y24 is 1.12 million electron volt, 7.6 million electron volt respectively, the energy released. So, actually the concept for the previous problem we will get clarity here. So, here whenever these two nuclei fuse to give a heavy nucleus, in case of the reactants what happens is the energy will be absorbed, that is the total binding energy if you calculate, that is the energy required to break the nuclei into nucleons. And in case of products, a nucleus is formed. In the formation of the nucleus, the total binding energy is the energy released. We have to compare the energy, total energy absorbed for breaking the nuclei into nucleons and energy released in the formation of nucleus from its constituent nucleons. So, if you check both of these, then we will understand whether energy is absorbed or released in a given nuclear reaction. So, as I told you here, we have to say this is energy required to break, energy absorbed otherwise, to break the nuclei into nucleons. That is nothing but 4, because there are 4 nucleons, 4 times binding energy per nucleon is 1.12 million electron volt, 1.12 million electron volt, that happen to be 4.48 million electron volt. So, in this case energy is released. So, energy released is total binding energy of it, released. So, energy released is 4 nucleons are there, and the energy released for this is binding energy per nucleon, so times 7.6 million electron volt. So, that happened to be 4 6 are 24, 4 7 are 28, so it is 30.4 million electron volt. Okay. So, if it is 30.4 million electron volt, this is the total energy released, this is the energy absorbed. So, net energy released is the difference of these two. So, therefore, energy released is given by, it is 30.4 minus 4.48 million electron volt. So, that happened to be nearly 26 million electron volt. Okay. So, this is it. Let us see the next problem. It is if 200 million electron volt energy is released in the fission of a single nucleus of uranium 92-235, how many fissions must occur per second to produce a power of 1 kilowatt? Now, we are talking about the power of a reactor. Power of a reactor is given by, it is if you are asked to talk given in terms of the number of fissions, it is a number of fissions into energy of each fission, energy released in each fission is the total energy released, and time taken for this process to take place is T, then we can say here the power of the reactor is given by, it is number of fissions into energy released in each fission divided by time taken. So, here power is given to be 1 kilowatt. So, we want to find out the number of fissions per second, so N by T, and energy released in each fission is given to be, it is not it is 200 million electron volt, that is 200 times 1.6 into 10 power minus 16. I am using that, I am not writing million electron volt as this. So, because I have some convenience, so 200 it gets cancelled 5 times, I mean to say all this. So, N by T is equal to, it is 1 by 1.6 into 10 power minus 19, it is 1 by 1.6 into 10 power minus 19. Already I told you we can make use of this simplified value 6.25 into 10 power 18 divided by 10 power 6. So, nearly it is, again there is a 5 here. So, 6.25 times 5, 6.25 times 5 is 31.25 into 10 power 12, 10 power 12. So that is approximately, that is 3.125 into 10 power 13. We better make use of this shortcut simplifications so that we can arrive at the answer quickly. Then let us see the problem. The power obtained in a reactor using U-92-235 disintegration is 1000 kilowatt, that is 1 megawatt. The mass decay of uranium-92-235 per hour is. So here we are talking about the power of the reactor, but mass decay. Mass decay, there can be two choices, that is complete annihilation of mass and mass converted into mass in the fission process. Okay. Complete annihilation, if it is required, then you have to write it as delta m into c square by t, where mass defected, mass completely converted, annihilated into c square by t. So you can arrive at that, that is 10 power 6 is equal to, that is mass defected or mass converted or annihilated times 9 into 10 power 3 into 10 power 18 whole square is 9 into 10 power 6 by, it is 1 hour, it is 3600 seconds. So obviously it is 400. So therefore this many we get it to be in kg because we have taken in SI. So delta m is equal to 4 into 10 power 8 by 10 power 16. So that is 4 into 10 power minus 8 kg. Okay. So that is, it is 4 into 10 power 8 by 10 power 16, 10 power minus 8, you get it to be equal to, you get this to be, it is, none of the answers is correct here. Okay. So it is, what we get here is microgram. Let me say, so this is nothing but 4 into 10 power minus 5 gram, that is 40 microgram. I'm sorry, that is 40 microgram. So this is the correct answer. Okay. So that's all. So this must have given you a brief idea of these three topics what I have discussed so far. Thank you.